Welcome to The Explainer. Today, we're going to decode these super powerful computer simulations that make so much of our modern tech possible. You know, everything from the phone in your hand to the satellites way up in orbit. I mean, it all comes down to controlling these invisible electromagnetic waves. But trying to predict how those waves are going to bend, reflect, and interact with complex stuff, well, that isn't just difficult. For a long time, it was pretty much impossible. In fact, engineers actually have a name for this challenge. As Keysight Technologies puts it, it's often seen as a dark art. And why? Well, because trying to solve the fundamental physics, the famous Maxwell's equations, by hand for real-world devices with all their weird shapes and materials, yeah, that's just not going to happen. So how do we solve these seemingly impossible problems? How do we turn this so-called dark art into a predictive science? All right, let's dive in. The answer is something called computational electromagnetics, or CEM for short. So instead of trying to find a single, perfect, exact solution, we use the incredible power of modern computers to calculate approximate solutions that are super, super accurate. It's really how we make the invisible visible. Now, while there are a bunch of different techniques out there, the world of CEM is really dominated by three major methods, or solvers. You can think of these as the primary tools in every electromagnetic engineer's toolkits. First up, we've got FDTD, which stands for Finite Difference Time Domain. This technique basically chops up space and time into this grid of tiny steps. It calculates the electric field at one moment, then the magnetic field at the next, over and over again. It's kind of like shooting a high-speed video of the electromagnetic waves as they travel and bounce all around the structure. Then there's FEM, the finite element method. Now, what's really cool about this one is its flexibility. It's absolutely brilliant for handling complex shapes because it breaks down a huge problem into a mesh of thousands of little manageable chunks, like tiny triangles or pyramids, and solves the equations for each little piece before putting it all back together for the full picture. And finally, we have MOME, the method of moments. This solvers is incredibly efficient, especially for problems with a lot of open space, like an antenna broadcasting out into the air. See, instead of modeling all that empty space, it just focuses on the surface of the object itself, calculating the electrical currents flowing right on it. Okay, so we've got these three powerful tools. But how in the world do you know which one to use for a specific problem? Well, a lot of it boils down to the kind of answer you're looking for, and specifically whether you care more about time or frequency. And this right here is the crucial distinction: time domain versus frequency domain. Time domain analysis, which is FDTD's home turf, is like watching a movie. It shows you how a system responds to a sudden pulse over a period of time. Frequency domain analysis, where FEM and MOM usually live, is more like a single photograph. It answers the question, okay, once everything is settled down, what does the field look like at this one specific frequency? So with that huge difference between time and frequency in mind, let's take a look at how you'd actually go about choosing the right solver for the job. We can actually break down the strengths of each method in a pretty simple way. And this table just lays it out perfectly. FTTD is your go-to when you need to see how a whole range of frequencies behaves over time. Think about something like a lightning strike hitting an airplane. FEM is the absolute champion for complex, enclosed things with lots of different materials inside, like simulating what's happening inside an MRI machine. And MOM? Well, that's the most efficient choice for open problems, like figuring out the exact radiation pattern from a satellite dish that's beaming signals out into deep space. You don't have to model all of space, just the dish. So, the most important point here is that these aren't just some abstract tools for academics. Not at all. These are the engines running behind the scenes, making it possible to design and perfect the technology that we all depend on every single day. Let's make this totally real. The phone in your pocket, CEM is used to design those tiny, super complex antennas that have to give you a perfect signal no matter how you're holding it. Or think about stealth technology. Engineers use these simulations to perfectly shape an aircraft to scatter radar waves, making the plane almost invisible. It's also absolutely critical for making sure the billions of tiny components on a computer chip don't interfere with each other, and for developing the advanced magnets in an MRI. CEM is the invisible engine that drives all of it. So it kind of leaves you with this thought. As our technology keeps getting smaller, faster, and more complex, what new challenges are going to demand even more from this dark art? And what amazing breakthroughs will be unlocked by the next generation of these incredible simulation tools? Thanks for watching.